Okay, ladies and gentlemen, today you are going to take notes using this video lesson, and these notes are going to get taped into your notebook. And what you get to do with the video, obviously, if you need to pause, if you need to rewind, you could really personalize your learning in case you need to go to a different speed. So, you need two papers in front of you. You need this full-size sheet that we're going to get to a little bit later, and you need this half sheet. And this half sheet has the stuff we're going to talk about first. So we've already talked about unit rate. We've talked about constant of proportionality with this unit. So what we need to do now is we need to talk about how we use those things to do something called scale factor. You've probably heard of scale factor before. Scale factor is like if there's a scale on a map. The scale is important so that you can tell how far apart, let's say you have two cities on a map. You really want to know how far apart they are, even though they might be only an inch or two apart on the map. You want to look at the scale of the map to see how many miles that really represents. So sometimes we use maps. More often than not, we use different figures for, let's say, a geometry problem. That's why this other paper has a lot of different shapes on it. We use scale factors sometimes to talk about how an image can be made larger or made smaller. So on this graph, what there are is there's two different rectangles. And first, Celeste drew the large triangle. And then she drew a new image which is smaller than the original triangle. So what we do when we look at the measurements that are given to us, or the dimensions of the object, we're going to have to compare the width and the height of each of our shapes, and then what we could do is use these numbers to come out with our constant of proportionality. So when you're looking at the original rectangle that was drawn, I would consider the width to be down here. And if you look, it seems to be 6 boxes wide. So you're counting from this side to this side. And each of those little hops, or sometimes we call them bunny hops, would be 6. And it might be centimeters, it might be inches, we don't really know. So we're just going to leave it 6. And then the height of that object, you can see that it goes all the way up. And each box, according to the scale, is 1 unit. So we're going to have a total of 18 units if we draw those bunny hops all the way up. So I'm just going to put 18 in the chart. So now, I just did something wrong. The original shape is supposed to have the height here. And we'll get rid of that real quick. There we go. Now we can work on the new image. The new image, we need to measure its width and its height. So the new shape is right here. It's only got 3 boxes across, and it's got a height, let's see, all the way up to, it looks like 9. So again, if we had drawn all these little bunny hops, we would have a height of 9. Now this one's pretty simple to figure out. Obviously they took the original and they reduced. So a reduction is the type of scale they did. And remember how we find our constant of variation. We take our constant of proportionality in a table. This is typically your x and your y. So if we take our y value and we put that value here, the new image's width is 3, the old image's width is 6, and we see we have a half. If you wanted to test the other dimensions, the heights, we could do that also, and you'd end up with the 9 from the new and 18 from the old, and it's still a half, okay? So we can see that what was done is they reduced the figure, and it is half as big. And are the corresponding lengths proportional? Yes, we just showed that they both came out to be the same constant of proportionality. And then again, down here it asks, what is the unit rate or constant of proportionality? And again, that was the 1/2 that we just calculated up there. And that means we would have to multiply by a half if we started with an original figure and we wanted to end up with a new image. So, now what we have to look at is my favorite thing, Oreo cookies. Okay, sometimes Oreo cookies, the originals are really good. They make miniature, mini-sized little Oreos, and those are pretty good too. But what I am hoping to find someday is where they make really, really big Oreo cookies. So you can see how scale factor works when we're talking about this side. Scale factor is what we would multiply by to either enlarge the Oreo and make it much bigger, or in the case of where they make the mini Oreos, make it smaller. So we have this little formula here that we're going to use when we want to calculate scale factor, okay? And it's really just our constant of proportionality formula with the y over x, but sometimes we have to look at see which shape is the new shape, which shape is the old shape. So we're going to put the new over the original each time, and you see how I have my pictures labeled. So the problem is we don't have any boxes to count like we did on the other side when we had those rectangles graphed. So what we're going to do is we're going to take a ruler, and we're going to take the side that is centimeters. And I think what we're going to do is we're going to measure the diameter. I think it's pretty easy. If you go right through the word Oreo, I think we can figure out how long. This one looks like it is probably I'm going to say it's about 3.2. I kind of made a mess there with my marker. So the diameter is 3.2 centimeters. And I'll just double check on this one. Yep, still 3.2. But the larger Oreo, if we were to find one of these made a lot larger, that one looks like it's going to be about, I would say 6.7 centimeters. And when we got the ruler handy, let's go ahead and measure that little tiny mini Oreo. And this one I'm thinking almost 2, so I better go with 1.9. The diameter of this one is 1.9. So now that we have all of our measurements, what we can do is we can find the scale factor. What was the amount they multiplied by to make this big Oreo? I'm going to guess it's about double the size, especially looking at my numbers, but I don't think it's exactly double. So let's do the actual calculation. My new Oreo's diameter is 6.7. My old Oreo's diameter is 3.2. We'll grab our calculator. Luckily, we don't have to do long division with our decimals, so let's see. We get 2.09375. So we were close in saying that we thought the scale factor was exactly 2. It's actually just a tiny bit more than 2. So let's see what we find out with our scale factor on our mini Oreo. Our new mini Oreo is 1.9. The old was 3.2. So if we divide that out, 1.9 divided by 3.2, this one is a little more than a half. See how it's 0.59375? So my guess for this one would have been that they take the original Oreo and they cut the dimensions in half, but it's actually a little bit more than a half as far as the scale factor is concerned. So if you can find scale factor with rectangles, if you can find scale factor with circles, well, guess what? We can find scale factor with any old shape. So what I found for you first are some triangles, and there's 2 lines you'll notice on this paper. First, we have to tell whether it's an enlargement or a reduction. So if you compare your original, you can see that it was enlarged to make the new. And then the second line where it says part B, this is where you find your scale factor. So guys, remember, this is the formula we're going to use. It's still constant of proportionality, y over x, but to help us, we have our new over our original, which is going to help. And then you'll notice that there's some multiple numbers on here. What matters when you're doing scale factor is you pick the sides that go together. So the left-hand side and the left-hand side could be what we use. Or if you much prefer using the slanted side on the right, you can use those 2 numbers. I kind of like them better, so I'm going to use them. The new has a 16 on top. The old has a 8. And if I reduce that, there's my scale factor. This is just doubled. You can see that with the other numbers as well. 3 doubled gave us the 6. So this shape over here, if you compare the original, it's actually a little smaller again than the other one. So we know this is an enlargement. And again, when you want to figure out your scale factor, we've got to be careful that we put our new dimension over the original. But again, we have 2 choices, okay? What you don't want to do is compare this side on the top right with this number on the bottom right, okay? Those sides are not called corresponding sides. what you want to do is you want to compare sides that kind of match up. Like if this was to get enlarged, it would turn into this side here. So this is the better side to use, 48 over 40. And if they don't reduce nicely, you know you can always use your calculator. Okay, this one gives me a scale factor of 1.2. So it is enlarged just a little bit, and that's how you get your scale factor. Finally, with number 3, you can see we have a reduction. So remember, that's the top line. Tell whether it's an enlargement or reduction. And then you have to pick some corresponding sides. So for this one, it looks like I'm going to pick the left side because I can see on the original how it was shrunk down just a little bit to form 40. So I'm going to go new over original. And you can tell this is absolutely upside down, or the reciprocal of the last one. And then we have a fraction, or excuse me, we have a decimal value that repeats forever and ever. So remember, when you write it down, use your repeater bar over top of that repeating digit. So your job is now to pause this video. You are going to finish the last 3 questions. When you're done, hit play again, and you'll be able to check your answers, and I'll show you where to tape these in your notebook. Okay, welcome back. We've already done the first 3 questions together, and you paused the video so that you could try a couple on your own. So let's check our work. For question 4, you enlarge the original figure to form this. If you used the sides of the triangle, you put the new over the original, 12 over 8, to get your scale factor of 1.5, or if you use the bottom, you put the 21 over the 14, and notice how you have the same scale factor. If we didn't have the same scale factor, it wouldn't be the true scale factor, just like a constant of proportionality has to be a constant value among all your variables. So for this one, the original shape was on top. You can see it got reduced, so this is a reduction. You can either use the bottoms of the triangle, so we put 35 over 42 in one example, or you could have used the right-hand side and put the 15 over the 18. Either way, we get that crazy scale factor again of 0.83 with the 3 repeating. And for the last one, it's another reduction. We could have used the bottoms, so put new over the original, or we could have used the right-hand side, new over the original. And let's see, if I did it correctly, they both agree to give us 0.8. So now, guys, what you're going to do is you're going to fold this in half. The half sheet itself is real simple, okay? You're looking at page 101 and 102 for your scale factor, so make sure you put your title. This page here that we want to be able to see our Oreos on the back, you can go ahead and tape right here on the left, and that way it flops open. And then this page here that we just folded in half, you need to tape that in also just on the left, and that way this will open up and you'll be able to see the whole page. See if I can give you a big shot of the whole thing so you know how this looks. Let's just get my bookmark out of the way. And when you're finished with this, please go and try the links that I gave you in Google Classroom. The links will take you to a couple websites that get you to practice questions on scale factor.